Welcome to Geolytics. It is now August of 2023, and it's been 3 years since we launched the platform. It's also been 3 years since we first recorded our explainer videos on typical GPR applications and processing within Geolytics. And over those 3 years, there have been tremendous improvements in the platform and additional features that have been built into Geolytics. So it's high time that we record some new videos. Today, we're going to be talking about an application related to geological layer mapping, which is a typical application for GPR. Now, the data set today comes from Concrete GPR in Eugene, Oregon, in the United States. This data set happens to be useful for us to map geology, to map rebar or bridge deck analysis, as well as pipes. It's quite a versatile data set. Today we'll look at geology. Now, when we look at the Geolytics platform, it's very similar to a Windows Explorer or a Mac computer where you'll have a root directory. And within that directory, you can have folders or directories that could be organized by client, by geography, by date, by year. I personally do it by client usually. So I've created a new folder for Concrete GPR in Eugene, Oregon. And within that folder, I can add other folders. But in this case, I have one project, and that project is sort of akin to a Word document or an Excel spreadsheet. It is a file that contains all of your information for that project. And I've called it Geological Layers. So let's pop into that. And what we see here is our layers, which is very similar to a GIS application. We only have one layer so far, it's GPR profiles. And to save us some time, I've already loaded in quite a few of the profiles. Now, this data set is generated by a GSSI 350 megahertz hyperstacking system. So these are DZT files. I have not loaded in the last two files, or the last two profiles, which in the case of GSSI actually consists of two, or actually four files, so two each. There's a DZT file and a DZX file. I'm going to take those four files and literally drag and drop them into the import window. The Geolytics platform will look at them, confirm that they're GSSI files and they're valid, and bring them in the correct place in the directory. Great. So we've got all our data uploaded into Geolytics. Now, what do? We need to figure out where we are. Now, there are two types of projects within Geolytics. One, which is GPS captured, so it knows where it is in live positioning, and that could be a total station. In this case, this is a traditional grid survey. Now, coming from the United States, this survey was collected at line spacings of 1 foot in the X direction. All of the X lines go from left to right, and then at 2 feet spacing in the Y direction, and those go from the bottom to the top. So we kind of have a sketch of what this all looks like. Let's try and recreate that within the Geolytics platform. So we have lines in two directions, X and Y. So I'm going to add a new folder here for my X. Confirm. I'm going to go back to my default folder, and I know from my notes from the field that files 10 through 42 are in the X direction. So I'm going to grab 10 through 42. I'm going to hold down my Shift key so I select them all, and then I'm just going to pull them down into my X directory. There we go. So now I have everything in the X directory. Now, I could simply rename this default folder to Y, but because this is an explainer video, let's add a new folder and call that Y. And we'll go to our default folder, and that is, yes, 43 to 91. And we're going to go ahead and drag that into our Y directory. So you can see that our default folder now disappears because there's nothing in it, and there's an X and a Y folder. The X folder contains the X files, and the Y folder contains the Y files. Let's go into positioning. So now we need to tell the platform where everything is. Well, the first thing we want to do is tell it the trace separation. Trace separation tells us how far apart the traces were, and we can manually enter that in as a number. But the GSSI file format includes an embedded trace separation, and that is gathered by the odometer. So if we trust the odometer and we believe it's calibrated correctly, then we can go ahead and select the embedded trace separation. If there is a compensation to be made, that is, if we know the odometer is 2% off, we can add that here as well. But right now, we'll do it as the odometer. Now, the other thing we know is that these lines are at 90 degrees because these are the X lines, right? I'm in my X directory. So I'm going to type in 90 here. And the last thing I need to do is tell it that I'm in feet and that I am 1 foot apart for each profile. All right, so here we go, except I got a problem here. According to my notes, the first file, which happens to be file 10, is actually at the bottom, not the top. And if I click on this one, I can see that, oops, line 10 is at the top. So I need to flip this around, and all I do is press that button, and everything's flipped around. Great, so now I've got my X files in the right place. Let's go to the Y folder. Okay, same thing. We're going to do embedded trace separation. And in this case, it is 0 degrees. And we're going to do a profile separation, in this case, of 2 feet. So now, once I put that in there, everything should look like my sketch, which, trust me, it looks like my sketch. Right, so, well, wait a minute. There's no data here. All right, that's right. So GSSI data, and some GSSI, other manufacturers have the same issue. When we look at 32-bit data, we are actually showing all 32 bits on the screen. But if the manufacturer is only saving files at approximately 15, 16, 17, 18 bits, then what happens is most of that data is clustered around the middle of the dynamic range, which means in this case, because we're using a grayscale, that everything looks gray. So if we go to our processing tab right here, there's actually a warning. It says, hey, this profile contains very low amplitudes. If you want to see it, press constant scale. So we press that and hey, there it is, great. So what's the first thing we need to do to this data set? We want to do a time zero correction. We want to get rid of that space in there because that is, well, not really existing, right? The ground surface is here. That's the first arrival from the transmitter to the receiver. And that's very simple. We'll go to add new process, time manipulation, time zero correction. And that works. Great. Now we want to add a little bit of a gain because it's kind of hard to see this. So we'll add a new process, gains, and we like to use energy decay. It's similar to an SEC gain if you're a sensors and software user. And usually we smooth it a little bit. Okay, great. So this is what I wanted to get to, right? I want to show you this really nice geological horizon here. Now, is it geology? Well, it might be. It could be the base of a slab. Actually, the base is probably underneath those hyperbolas of the rebar, but let's call that geology. So I want to map that. I want to map that over this entire concrete slab. Okay, maybe that's my project. So let's go ahead and do that. How am I going to do that? Well, the first thing I'm going to do is I'm going to add a new layer to my GIS section, call it a horizon interpretation. Maybe I'll give it a name and I'll say, I don't know, Geology 1. And I want to give it a bit of a color here too. Let's go for a light green. Okay, hopefully that'll turn up. And here I go. I'm going to take Edit Horizon and I'm going to start drawing this in, right? I'm going to try and be as accurate as I can within reason. And here we go. Now, where does it go? Well, let's just assume it's the lowest horizon we can see here. Okay, done. All right, well, that's our first line. That's great, okay? But wait, it's all green here. That doesn't really help us. Well, let's add a little bit more information to this model that we're building. The first thing is, let's go back to our GPR profiles and get a velocity here. So this is a really nice pipe. Let's use that and let's guess at a velocity of, well, about 9.3. Okay, now we can convert everything from time, two-way travel time, to depth. And if we go back to our geology layer, double click on that, we can start drawing out a little depth scale here. Oh, okay, that's neat. Okay, let's go to the next one. Whew, this is going to take a long time, isn't it? There's got to be a better way, and maybe there is. So what you want to do is go to this one where it says Auto Discover, use that icon, and let's see if we can get the computer to draw the line for us. Now, it's not the cleanest of lines. We're seeing through rebar here, but we have a pretty good estimate here that, yeah, we can kind of get it reasonably well. And when you like it, you accept it, and maybe you want to smooth a couple things out. Okay, that's great. Now, see what's happening here. We're actually building up a heat map as we go along, right? So we see this little trench that was dug for this pipe probably. This is getting cool. So let's keep going, and let's go to the next one. In fact, let's skip a few because this will take forever to do this. And I'm going to use the automatic picking tool again. And what I do is I just add a few little... No, actually, I do want to go down here. I want to take that one away, that one away. So you can see what I'm doing is I'm kind of seeding it and then just going in and sketching it a little bit just to correct it. Once I like it, I'll go to a few more. Okay, let's do that again. And of course, the cleaner your data set, the easier this process is. One of the best applications for this automated layer picking algorithm is for ice thickness, of course. When you have ice going into water, it's usually a very, very clean, nice surface, and you can trace that for many, many kilometers at a time quite often. So quite a few of the users use this for ice road mapping. So I'm going to do one more here just to kind of complete this because I want to build a model out of this and I don't want to take too much time going over each one. So that's reasonably okay. Yep, we'll accept that one. All right, great. Now we've got a very deep area there. That's great. Now I want to do some of these north-south lines, or the up-down lines. Well, one of the original problems with doing this with GPR is you could never get the crossing points right. So what we've built in is a little warning for you, and you can do this manually. You can draw along, and what you want to do is hit the bottom because that is the exact crossing point that we've already got on the other profiles, right? So you can make sure that your final surface that you're going to build is as smooth as possible because at each crossing point, you know you've hit it correctly. I'm gonna pop over here, do another one, maybe, well, I guess okay, we'll do it manually. Okay, we'll just sketch this along here. All right, well, I don't really have enough data to make a surface, but maybe I'll do one more, and I'll attempt to make, I've obviously made a mistake here. You can see that I should go back to that bottom one and pick the right phase. I've probably missed it in my haste, but you can probably argue it goes down here, but anyway, you get the idea. Okay, so now let's say I want to build a surface out of this. Now, I think I should probably do a couple more of these just so I can have a more complete surface. And even if it's wrong, it doesn't matter. Okay, well, something like that. And I'll do one at the top. All right. Here we go. Yeah, I haven't been very precise on this, but that's not the point of the explainer video. Okay, good enough. And what I'll do is I'll do maybe, okay. Let's see what we can do here. Next, I'm going to add a layer, depth grid. Okay, let's do it. We'll do depth scale. And in this case, I'm going to have to make my search radius really, really wide because I have so many gaps in my data. Normally, I'd try to do it on every one, of course, and I will open up the cell size perhaps as well. So let's see what happens. Oops, geology is the one we want, and hopefully we can make somewhat of a grid. There we go. All right, so we made a grid, which is fully 3D aware, of course. All right, we can see that all in 3D. And there we go. So had we georeferenced this and give it a lat long coordinate, we could simply export everything as KMZ file. Right now we can do CSV, of course a DXF surface, we can do a surfer grid or an image file that actually does have a coordinate file that goes along with it for GIS applications. So that's how we would map geology within geolytics. Thank you very much.